welcome to this math lecture video. I'm going to start off the semester by talking to you about linear equations and one variable. This may be review for some of you. It depends on when you last took math, how you're going to find this material. A nice thing about the video is you can play it faster. If you want me to talk faster, you can set my speed up to 2 times speed, or you can watch it again if you wanted to go over the material again. So in this video, here's our agenda. I'm going to give you a definition for linear equations in one variable. I'm going to show you how to solve equations in one variable algebraically. And I'm going to give you some more definitions for consistent, inconsistent, and conditional equations. Those are all types of linear equation in one variable. So a linear equation in one variable is the equation of a straight line. When you graph this kind of equation, you get a straight line. And it has a few characteristics that can help you determine just by looking at it that it's a linear equation in one variable. We'll go through that. So this is a nice little definition. Linear equation in one variable. And I'm going to give you guys some examples. Here are some linear equations in one variable. You could have something like 3x equals 2x plus x. You could have something like 5x plus 2 is equal to 3x minus 6. You could have something like 5x minus 15 is equal to 5x minus 20. You could have, I'll give you one last example. This one we'll solve at the end of the video. 4 times x minus 3 plus 12 is equal to 15 times x plus 6. So these are all examples of linear equations in one variable. And you know that there are linear equations in one variable for a few reasons. The one variable part, I think, is pretty easy to see. If I look at each of these equations, I only have one variable, x. I could use another variable like a or y or z if I felt like it. And as long as you can only identify one variable, you know that this is an equation in one variable. But how do I know if it's linear or not just by looking at it without having to graph? It turns out that the exponent on our one variable here, remember, you may or may not remember from a previous course, the exponent is a number that goes up here. And when you don't write an exponent, it's understood that we have an exponent of 1. So look at all of these exponents here on our variable. All of these have an exponent of 1. And that's one way that you can know these are linear equations in one variable. Now, some of these linear equations in one variable are a little bit strange. And I want to go over those and give you some examples of why they're strange, and we can use them to define those terms that we wanted to talk about. So here I've defined for you linear equations in one variable. Check! This is a good definition to start with. We're going to do some solving, and in the process of solving, we're actually going to define consistent, inconsistent, and conditional equations. So we're going to do this example highlighted in green first, and it turns out that this is going to be what you call a consistent equation. Consistent equation. So let's solve. We have here 3x is equal to 2x plus x. When you're solving a linear equation in one variable, you want to use your rules of algebra to bring the variable all together and to consolidate your like terms. So what I notice here is I have like terms 2x and x. So because those are like terms, I can add them. And then I'm left with 3x is equal to 3x. You might look at it at this stage and go, well, duh. Yeah, 3x is equal to itself. That is actually what makes this a consistent equation. Whatever value I put in for x, this is always going to be true. I'll show you what I mean. Suppose x is equal to 2. So then I would write 3 times x is equal to 3 times x. And I would plug in my value of 2. So I would have 3 times 2 is equal to 3 times 2. And that would give me 6 is equal to 6. And that would be true. That's a true statement. Suppose I change my value for x. Suppose I say x is equal to, I don't know, 4.5. And then I would plug in 4.5 for my value of x. And I would know x is equal to, what is it? Let's see, 4 times 3 would give me 12. And then 3 halves is 1.5. So I'd get 13.5 is equal to 13.5. Still a true statement. And you might see the pattern here that I could choose literally any value for x. I could say x is equal to a gabajillion. That's not a real number. Let's pick a real number. Let's make a nice big one. X is equal to 7,564. 7,564. I don't actually have to do this multiplication at this point. I think you trust me that if I take a number and I multiply it by the same other number, my answer is going to be the same. So you would call this a consistent equation. Consistent equation because it is true for any value of x. That's a consistent equation. Let's take a look at our second example that we had here. This one is what you would call a conditional equation. Let's solve this guy in blue. So we have 5x plus 2 is equal to 3x minus 6. This is going to turn out to be what you would call a conditional equation. And I'll show you how you would know that. All of these, you're going to figure out the type of equation they are by solving them. So let's have the same instructions here. And let's say we're going to solve 5x plus 2 is equal to 3x minus 6. So my goal when I'm solving a linear equation algebraically is I want to isolate my variable. I want to get all my terms involving a variable on one side of the equal sign, and I want to have everything involving a constant on the other side. So that's what I'm going to do here. I'm going to start off by targeting my variable term. I see that I have a 3x here, a positive 3x. So the opposite of positive is negative. So to undo this positive 3x, I'm going to subtract 3x from each side. So on the left-hand side, when I subtract 5x and 3x, I'm left with 2x plus 2. And here, when I take positive 3x and I add negative 3x, I get 0 minus 6. And I have 2x plus 2, and I can simplify 0 minus 6 and say negative 6. Some of you are wondering, do I have to write this step? No, you don't have to. I'm just showing you because I'm a math teacher. You just have to show enough to make your argument clear to your audience. So I'm showing a lot because my audience is math students who maybe haven't taken math in a while. But when you're writing your work to show me, you can show me less work because I'm your audience. Most of the times when you're doing math in my class, your audience is going to be your classmates. So you want to show them as many steps as you can. All right, so here we are. Now I have 2x plus 2 is equal to negative 6. So I'm going to subtract 2 from each side here. So that I can, again, I'm just trying to get these x's by themselves. So I have 2 subtract 2, which cancels to 0. And I'm left with 2x is equal to. And I have negative 6 minus 2. This gives me negative 8. Now I need to pay attention to how 2 is modifying x. So here, when you have two numbers written next to each other like this, what this means is that I'm actually taking 2 and I'm multiplying it by x. And because the opposite of multiplication is division, I want to undo the multiplication of 2, so I will divide by 2 on each side. And so here I have 2 divided by 2, which is equal to 1x. And on the right-hand side, I have negative 8 divided by 2, which is equal to negative 4. In math, when you have a coefficient here of 1, you don't need to write it. Just say x is equal to negative 4. So what this means is that our statement is only true when x is equal to negative 4. So 5x plus 2 equals 3x minus 6 is only true if x is equal to negative 4. That's what makes this conditional. This is true on the condition 5x plus 2 equals 3x minus 6 is true on the condition that x is equal to negative 4. And that's why you would call this kind of equation conditional. Most equations that we're going to talk about and deal with are conditional equations. Let's talk about an inconsistent equation. These are my favorite type because they're strange. And I like strange things, you guys will see. So you get to know me throughout the quarter, or the semester rather. You'll see that I really enjoy when math does something unexpected or strange. So these, this one is called inconsistent. This will be an inconsistent equation. Let's solve it. That's how you'll see what's inconsistent about it. Maybe you see it already. So we're going to say solve. Notice I'm using the same tactics. Every time I try to solve something, I follow the same steps, trying to isolate my variable. And maybe you have experience with that, and maybe you don't have very much experience with that. That's okay. We're going to learn together in this class. So we're going to try to solve this, and just like before, we're going to take our variables and try to move them to one side of the equation, and take our constant terms and move them to the other. So for instructive purposes, that is to teach you something, I'm going to start with the constant terms. You can start either place when you're dealing with addition and subtraction. You could start with the constants, or you can start with the variables. But I see I have negative 15 on the left-hand side. So the opposite of negative 15 is positive 15. This is called your additive inverse. If I add a number to its additive inverse, I get 0. When I add negative 15 and positive 15 together, I get 0. So on the left-hand side, I'm left with 5x. And then on the right-hand side, you might have to use a little bit of caution here, depending on how you feel about negative numbers. But I have negative $20, and I'm adding $15. So let's say I owe $20 to a friend. I find $15 on the ground. I give it to my friend. I still owe them $5, right? That negative 5 kind of represents the debt there. And now we're up to the part where the strangeness of this equation will be obvious to all of you. We're going to try to isolate our variable. So, okay, the opposite of a positive 5x is a negative 5x. So I'm going to subtract 5x from each side of this equation. And I get 5x minus 5x. Well, that gives me 0. 5x minus 5x. Well, that gives me 0. And so now I'm telling you 0 is equal to 0 minus 5. Or 0 is equal to negative 5. And you should tell me, what? No. 0 is not the same as negative 5. Those are two different numbers. So this is a false statement. And it turns out that that's what makes this an inconsistent equation. This is a false statement. An inconsistent equation is false for any value of x. So in other words, it doesn't matter what value of x is. 0 is never going to be negative 5. That's how you know this is an inconsistent equation. So I'm going to solve one more, slightly more complicated example, just for fun, and then we're going to wrap up this video. So let's say I wanted you to solve something like this. How I would say this out loud is I would say 4 times x minus 3 plus 12 is equal to 15 minus 5 times x plus 6. You can hear my daughter's toy in the background. That'll be a regular occasion when you're here learning math with me. She's 2 and she's very cute. I might show you guys her during class sometime. So here we have some parentheses to deal with, and as long as we stick close to our order of operations, we should be okay. So the first thing I'm going to do is use my distributive property here and multiply. Instead of taking 4 times this entire thing, I'm going to break it down and say 4 times x minus 3 times 4 plus 12 is equal to, and then I'm going to do the same on this side. We'll have 15, and I'll distribute that negative 5. So we'll have minus 5x minus 5 times 6. And then I can go through and simplify. That's 4x minus 12 plus 12 is equal to 15 minus 5x minus 30. This is kind of nice. Look, minus 12 and plus 12. Those cancel out to 0. Those are additive inverses. So we get 4x is equal to 15 minus 5x minus 30. So I see here that I have some like terms I can handle on the right-hand side. I know what 15 minus 30 is, or I can use a calculator to find out if I don't. Calculators are okay in this class, by the way. So 15 minus 30 gives me negative 15. And I still have that negative 5x to worry about here. So now I have 4x is equal to negative 5x minus 15. And I want all of my variables on the same side. So I'm going to address that by adding 5x to each side. And that's going to give me on the left-hand side 9x is equal to negative 15 on the right-hand side. Now I have to pay attention to how 9 is affecting x. So here 9 is multiplying by x. So just like how we have additive inverses that give us 0, we have multiplicative inverses that give us 1. So I divide my left side and my right side by 9. I'm doing division because it's the opposite of this multiplication that's happening. And I'm choosing 9 because any number divided by itself is equal to 1. And we get 1x is equal to negative 15 over 9. And remember, I told you, you don't have to write that 1x. That coefficient, we understand that in math. If we don't write the coefficient, we understand that coefficient is equal to 1. Now, you might want to be done here. In fact, I know that you want to be done here. But we have a fraction that we can reduce. And in this class, you should give all of your fractional answers in fully reduced form. We'll practice it throughout the semester. I know some of you are like, no big deal. And some of you are like, yikes, I hate it. Don't worry, we'll get it together. I'll show you how I reduce quickly in this video. I might make a separate video about it for more practice for those of you who want to know. But what I do is I factor my numerator and my denominator. So here I look at this as, oh, I have -1 times 3 times 5. That's all equal to -15. And in the denominator, I say I have 3 times 3. And wouldn't you know it, I have a common factor here, 3 and 3. And I just told you guys, a number divided by itself is equal to 1. So that's why I can draw those little slashes there. So we end up with x is equal to -5 divided by 3. And that'd be your final answer. And you could write it like that. That's all I have for you guys in this video. And in the next one, I'll talk to you about linear inequalities. And you should be ready to start doing your homework right away for some of these problems. Thanks, guys. I'll see you in the next one.